So our first speaker today is Professor Yoshinori Tokura, who is one of the world leaders in the study of correlated electron systems. He's known for his seminal contributions to the study of the Mott transition, high TC superconductivity, and especially for developing and exposing beautiful new physics in new materials. He's the head of the Correlated Electron Research Group in RIKEN, Japan, and a professor at the University of Tokyo. He's won many prizes, including the Magnetism Prize in 2005 from the American Physical Society. And in 2010, he was ranked in the top 10 most cited physicists of the last 3 decades, which is a pretty impressive feat. So let's welcome Tokura Sensei here. He'll be telling us about, in this first talk, about magnetism as an emergent phenomena.
First of all, I'd like to thank the Kavli Foundation and also this Symposium organizers, Professor Valence and McDonald, for inviting me to this wonderful occasion. And in my talk, I would like to overview the late advances in the magnetic property studies on the correlated electron system. But I have to confess at first, my view is very, very much biased. So according to the old Japanese proverb, I feel like looking at the ceiling from a lead. It's a very narrow scope. But let me try to focus on the 2 topics. The minor importance of the spin-orbital superstructures, where the physics of the Colossal magnetoresistance and the multiferroics are involved. And the second one in the relation between the magnetism and the topologies, which includes some Skymion or also the magnetic topological insulators. Let me start with this spin-orbital superstructures. As you know, in the correlated electron system, electron can gain the 3 attributes, namely the spin, charge, orbitals. And especially the entanglement between the spin and the orbital degree of freedom become very important. And its meaning is twofold. One is the spin orbital exchange interaction is entangled with each other, and also that we should consider the relativistic spin orbit coupling. And concerning the former issues, and of course, from the beginning of the study of the magnetism, this was recognized, but especially by the work by the Kugel-Komsky type, that they just introduced sort of the effective Hamiltonian with the spin and orbital degree of freedom with the couples. Maybe we should consider on the equal footing basis of the spin and orbitals. Sometimes in the ordered state, as you know, the spin and orbital show the ferro and antiferroic orders, respectively. And the typical example is seen in this kind of the perovskite, transition metal oxide. For example, the lanthanum VO3. You see the spin is just ferromagnetic along this axis. It's a C-type, chain-like antiferromagnetic orders, but the orbital, T2G orbital is staggered with each other, so G-type. On the other hand, in the yttrium VO3, a little bit change the lattice form. Then the spin is staggered, pi orders, but the orbital shows this kind of the C-type ferroic state. And even one better known example is the lanthanum manganese O3 within the AB plane. Orbital is staggered. This is the antiferroic order of the orbitals. Spin shows the ferromagnetic order on the AB plane. And this spin orbital entanglement can be seen typically in the so-called colossal resistive manganite. And in the, for example, the parent compound, we have this type of the rare type antiferromagnetic state where the staggered orbital is there. But when we dope the hole into the system, namely the band filling is changing, then this orbital state is melted. So the orbital disordered or quantum disordered, but a ferromagnetic double exchange type interaction dominate. So it's a ferromagnetic metals. But this double exchange type ferromagnetism show up at a different form in the 2 dimension, in the 1 dimension. In 2-dimension case, in plane show the ferromagnetic ordering where the ferroic order of the x square minus y square orbital is observed. With further doping hole or reduction of the band filling, we have a 1-dimensional ferromagnetic chain, but the orbital is a d square type ferroic orders. And especially between these 2 orders, compounds tend to show the keen competition. And the most known composition is a rather complex spin orbital charge ordered, what we call the CE type. Here the orbital show this kind of the staggered state, and also the spin also the antiferromagnetic ordered, charge ordered. But this state shows a very keen competition with the ferromagnetic metallic state with disordered orbital state. For example, in the some manganite compound, if we can change a little bit the composition, this composition change means the change of the electron itineracy or band width or electron hopping interaction energy. And then there is the ferromagnetic interaction charge and orbital ordered states suddenly under the melting and the ferromagnetic metallic state come. But important point is that this charge orbital ordering transition temperature and the ferromagnetic transition temperature meet at 1 point, forming the so-called Bicrticality point. And near here, we may have lots of chance of playing the game. For example, at this position, in the little bit insulating side, originally the compound showed the spin, charge, and orbital ordered state, so-called the CE type. But when we apply the magnetic field, phase is suddenly changed into this ferromagnetic metallic state, and also showing some Bicrticality point at 2 or 3 Tesla in the phase diagram, and the metal insulator to metal transition occurs up to the 200 Kelvin. On the other hand, in the ferromagnetic state, even in this state, just above this Bicrticality point, we have a lot of the fluctuation of the charge orbital correlations. Then the application of the magnetic field tend to drive the system to the ferromagnetic state. So the near here that we observe the huge magnetoresistance. That is the origin of the colossal magnetoresistance. So this kind of the spin orbital charge coupled physics show up in the manganite system where we can play a lot of game. Not only, for example, the application of the magnetic field shows a large magnetoresistance change, but not only by magnetic field, but also the application of the electric current pulse or irradiation of the laser light, pulse light, or even the X-ray irradiation compound undergoes the insulator to metal transition. Especially electric pulse induced insulator metal transition, and not on this compound, now can be used as a sort of the resistance switching memories early on. Okay, then we have another example of the spin orbital coupled structure. That is the physics of the multiferroics. Multiferro means the compound shows the co-current order of the ferroelectric order and the magnetic orders. In those compounds, we can enhance the so-called magneto-electric coupling. That means the electric field can modify the magnetization, and the external magnetic field can modify the polarization, vice versa. Especially this second term is very important for the spintronic application. You can manipulate the magnetism in terms of the electric field. But in order to gigantic this one, we need a spin-orbit interaction, a relative spin-orbit interaction. And because the electric polarization is a sort of the electric displacement of the electric cloud, and the spin the electron moment. So in order to combine this one, the spin-orbit interaction is very important. But once if you have a strong tight polarization and magnetization, then we can have a cross control. Namely, in terms of the magnetic field, you can change the polarization. And even more importantly, in terms of the electric field, we can change the magnetizations. And there are many or several schemes which can produce a multi-ferroic state in the materials. But I only show the one very prototypical one. That is sort of the spin current mechanism, or inverse Jarzynski-Morier scheme. Let's consider the neighboring spin are interacting with each other, but mutually canted. But in that case, we can view there is some spin supercurrent is flowing between the two spins. So this kind of the genuine spin current can produce the effective electronic polarization, P. Or you can see that this mutually canted spin, that this already breaks the inversion symmetry. So you operate the inversion symmetry operation, then the spin rotating sense is different. Effectively, the polarization is reversed. The meaning of this model is quite important. Namely, that if you have this kind of the transverse helical structures, then every two spin can produce the local polarization. So eventually, that all that rotating spin texture can generate the local macroscopic polarization. But when you reverse this polarization in terms of the electric field, then the spin rotating sense is reversed. So again, this magnetic structure, the electronic polarization is intimately coupled. And this was typically confirmed by the former manganese oxide compound, parent compound. Again, on the AB plane, we have a staggered orbital, then the ferromagnetic interaction is dominant. However, if you have a larger lattice distortions with the replace of the lanthanum with a more smaller rare earth ion, namely the terbium or dysprosium, then the same orbital state is interaction become important. This is the anti-ferromagnetic in nature. So the ferromagnetic J1 and the anti-ferromagnetic J2 are competing with each other to produce a rather long period in commensurate modulations. And at some temperatures, compounds show that this kind of the spiral modulations. So according to the polarized neutron scattering, and when the polarization is downward, then the spin is show the counterclockwise rotation, and the polarization is reversed by the external electric field. Spin rotation is clockwise. And this is show the temperature dependence of the electric polarization induced by spin textures, but it's very precisely proportional to the quantity of the S cross S, namely vector spin chirality representing the flow of the spin current. And so far, this cycloidal spin habit can generate the polarization. But of course, this is no net magnetization. In order to make it useful for the future device applications, of course, we need some spontaneous magnetization. In order to do that, you can simply add the magnetization, this quantity, this spin textures. So this is a conical spin texture. Still there, we have a cycloidal habit, polarization P, and also the magnetization is show up as average of this spin texture. So the one conical spin texture can generate the both polarization P. So automatically it's a very intimately coupled. So we can create this kind of the situations. And typically this kind of the transverse conical spin habit can be found in the rather old materials, historic materials, that is a cobalt chromium 204 cobalt chromite spinel compound. This state was studied by Professor Tom Kaplan. And this is the conventional MH curve, magnetization curve. But if you start a polarization state can be reversed upon the reversal of the magnetization, or starting from here, the vice versa. So by changing the magnetic field, you can change the polarization directions. Namely, that this kind of the spin habit is just turn over around this one. So the polarization direction is different. So like this, we have several important state variables or topological spin texture to host a magneto-electric response, namely this kind of the vector spin chiralities. Another important one is the so-called toroidal moment expressed by this quantity, R cross S. So in this case, for example, this kind of the spin in plane rotating habit can produce a polar moment, toroidal moment. But under the prudence of the spin-orbital coupling, LS coupling, this can be deformed to this form, namely the toroidal moment can work as a sort of the built-in vector potentials. So if we have this kind of the spin rotating habit within the solid, then we have a vector potential here, and then this vector potential can respond to the external electromagnetic field. It's called a very interesting linear and nonlinear optical response. The third one I would like to mention is a scalar spin chirality. This is a 3-spin correlations. And if 3 spin is mutually canted, forming the non-coplanar structures, then we can have a solid angles subtended by these 3 spins. So this 3 spin can generate the effective magnetic field. And the natural extension of this scalar spin chirality is the Skymion texture. Later I'll touch on. Okay, this is a very brief explanation of this scalar spin chirality is correspond to the emergent magnetic field. Let's consider if the 2 spin is mutually canted with each other and the conduction electron is strongly coupled to the underlying spin texture and by the sort of the hand rule coupling. Then of course, this transfer interaction magnitude is depends on the relative angle of the local spins. This is the essence of the double exchange ferromagnetism. But also this transfer can gain some complex phase factors. This is nothing but a very phase. So if you have 3 mutually canted triad spin structures, then the clockwise and counterclockwise moving electron can feel the different electronic phases. So this is very resembles the situation where we have a fairly large magnetic flux is penetrating on this triangle. So this effective magnetic field or emergent magnetic field can be expressed by, again, this spin chirality quantities. This is nothing but a solid angle subtended by the 3 spins. And actually, this kind of the transport effect due to this effective magnetic field was observed a long time ago, more than 10 years ago, for one of the pyrochloride ferromagnet. It's the most famous magnetic frustrated system. And as you know, the pyrochloride structure, usually there are 2 pyrochloride lattices. The one is Ising moment, show the so-called 2-in, 2-out structure due to the very strong spin-orbital coupling. But also this spin habit is transmitted to the almost ferromagnetic molybdenum spin. So the molybdenum spin also shows this kind of the 2-in, 2-out or umbrella-like structures. So this really shows the spin chiralities. And in accord with our expectations, if we measure the Hall effect, then there is an effective large fictitious magnetic field is there. Then with lowering temperatures, we are very rapidly increasing the Hall effect. This is very contrary to the case of the conventional anomalous Hall effect response. And even more importantly, if we apply the magnetic field and tend to saturate the magnetic moment, then the spin umbrella is tend to decrease. Then this topologically induced Hall effect is tend to decrease or almost vanishes. But when the field is applied along the 1-1-1 direction, it's a very special direction. So the compound show the so-called 3-in, 1-out or 1-in, 3-out structures. Then in this case, scalar spin chirality, its sign is different, opposite. So when we apply the magnetic field, originally the spin is 2-in, 2-out, but eventually the spin turns over to the 3-in, 1-out or 1-in, 3-out. Then the compound shows a negative response. So it's really magnetic field dependent crossover from the positive to negative scalar spin chiralities. So this similar idea can be also applied to the more real space version of the scalar spin chiralities. That is the Skymion. The Skymion is originally the concept introduced by Tony Skymion long time ago to describe the state of the nucleon. And he intended to model a particle as a sort of the topological soliton, something like a hedgehog and this kind of the Skyrmion natures. And again, the Skymion in my mind is something like this. And in the peripheral region, the dark region, the spin is going up. And coming to inside, the spin is rotating. And finally, it goes down at the core. So if you map all the spin direction into the single spheres, then these are all the spin direction just wrap the sphere. Namely, the solid angle subtended by this spin is 4 pi. So divided by 4 pi, we can have an integer number 1, so what we call the topological charge or Skymion numbers. So this is a rather continuous extension of this scalar spin chirality ideas. Importantly, the one Skymion corresponds to the one flux quantum. So if the electron moving on the Skymion texture, its coupling is so strong, in that case, it can give rise to this kind of the fictitious magnetic field, emergent magnetic field. Let's suppose there is a one Skymion per square nanometer, and the electron is strongly coupled, 100 coupled, to the underlying lattice, and then the effective B field, that the conduction electron field, is as large as 4,000 Tesla. It's a huge magnetic field can be realized for the conduction electrons. The stage of the Skymion is the most typically represented by the so-called mangan silicide or iron silicide type, this B20 compound. This is a very simple cubic compound, but its lattice structure is a chiral. Namely, there is a left-handed and right-handed enantiomers in these materials. However, in these compounds, the spin exchange interaction is almost ferromagnetic, this one. But due to the lack of the inversion symmetries, we should have some Jaroszewski-Moria vectors, and we have some second term, anti-symmetric term. This term tends to twist the spin state. So the spin is naturally show this kind of the screw structures. Actually, this screw structure period is given by the ratio of the J over D interaction. And typically in this compound, ranging from the few nanometer to up to 300 nanometers. Usually the ground state is in some bulk compound is this kind of the helical structure. But this helical structure is rather confined in the rather thin film or placed in the very special temperature and the magnetic field windows. Then sometimes the spin helical direction is restricted. For example, into 3 directions. So if you have a 3 direction multiple Q state is realized, then its simple mixture form this kind of the vortex-like core is just form the triangular hexagonal lattice. If you slice out one spin habit, this is nothing but a Skymion. And actually, this kind of the Skymion lattice or Skymion crystal state was first probed by the German group, Christian Preider and Achim Rosch and their collaborators in almost 5 years ago on the mangan silicide. And they just focus on the so-called A phase in the mangan silicide phase near the phase boundary and the magnetic field. And this compound was known as a very mysterious phase. And there are lots of the work. But in this mysterious phase, they found that this state corresponds to the Skymion, crystal Skymion lattice system in terms of the small angle neutron scattering. Neutron angle is scattered forward direction. Then they have a 6-fold low angle peak at k space. This corresponds to the Fourier component transform of this hexagonal lattice. But soon after, some Japanese group, including myself, just observed this Skymion lattice in the real space in terms of the Lorentz microscope. Lorentz microscope means they can only visualize the in-plane component. So it shows the originally the helical spin texture just show up like stripe features. But when you apply the magnetic fields along the normal to the plane, then this helical structure is suddenly condensed into this kind of the vortex lattice. So but if you scrutinize one vortex, this is the black region, the spin is going up, and the other region, the spin is rotating. Can I have some pointer? Oh, thank you. Spin is rotating and going down. Nothing but represents this kind of the Skymion textures. And actually, originally the Skymion phase is a very present in the very narrow regions. But in the thin films, and you cannot realize the screw state because in the thin plane, if you apply the magnetic field along the normal to the axis, Q vector tend to normal to the plane. But the film thickness is too small. Then they have no screw structures. So eventually the Skymion state is stabilized down to low temperatures. But even more importantly, for example, the Skymion show up, but even if we apply the further magnetic field, then the Skymion tend to evaporate from the system, but still there you can see the trapped, isolated Skymion. Because the Skymion is topologically protected, so it can be present as a sort of the metastable state. So actually, you see some movies, and originally the compound is this kind of the screw state. And this is monochromatic movies, but you have a screw state. But when we apply the magnetic field, and the magnetic field is gradually increased, then you observe the condensation of the Skymion from the thinner part. And then eventually Skymion crystal state is dominate over the samples. And finally, it showed a rather perfect crystallization of the Skymion. But with further increase of the magnetic field, Skymion is originally topologically stable, but still destroyed. And it's a forcedly linear ferromagnetic state appears. And eventually the ferromagnetic state is dominant over the sample. But even finally, we have some trapped Skymion at the thinner region. So the very important topic of this Skymion science is also that it can be driven by the ultra-low current densities. So originally, the cutting-edge technology of the spintronics is to drive the magnetic domain or magnetic domain wall in terms of the spin-polarized electric current, something like this. And in that case, the momentum is transferred to the domain walls, call it the spin transfer torque. But usually it needs some critical electric current density more than 100 million ampere per square centimeters. But in the case of the Skymion, this critical density is reduced less than even the 100 ampere square centimeters. For example, this is the original Skymion picture. You can have a lot of the Skymion, but if we apply the current, then you observe the Skymion suddenly disappears because the Skymion movement is so fast, so the picture cannot. I give up. So here I just summarize. And the spin-polarized current also drag the Skymion. But this spin-polarized current itself is deflected by the emergent magnetic field carried by the spin chirality of the Skymion. So it's nothing but a topological Hall effect. But due to the counteraction of the topological Hall effect, Skymion also shows another direction movement. And the Skymion also carries the emergent magnetic field. So its time dependence means the sort of the electromagnetic induction. So also we have an emergent electric field is observed. This is also confirmed by the Pryder and Roche collaborators. And concerning the topological Hall effect for the mangan silicide, and originally in the bulk crystal, it showed a rather narrow temperature and magnetic field regions. But in addition to the conventional anomalous Hall effect, they observed a narrow but very clear, fairly large topological holes observed. But even all the order, long-range order disappeared, and the compound undergoes some non-Fermi liquid regions. Even in that case, they observed a very large topological Hall component, perhaps coming from the topological spin correlation. This might be an origin of the non-Fermi liquid behavior observed in the mangan silicide above the quantum critical point. But this Skymion texture is not so simple, and sometimes also three-dimensional. And we think that this three-dimensional Skymion is also realized in the mangan germanite, and this can be this kind of the crystallization of the Skymion or anti-Skymion, or hedge-hodge or anti-hedge-hodge band. And in this case, in the strong correlation limit, we can consider the divergence B is also non-zero, and it's a sort of the magnetic morphosis. One slide. And another important thing about the correlation between the topology and the magnetism. Of course, people are very interested in the magnetic topological insulators. Skipping the detail, but the surface state is topologically protected and show the Dirac cone-like, where the spin and the momentum is locked with each other. And people observe some quantization of the Landau level in terms of the electric field, magnetic field. And of course, in that case, we should observe some quantum Hall effect from the Dirac fermion. But if this material can be made magnetic, we should observe the quantum anomalous Hall effect. That was predicted by the Suchan Zhang and Nagaosa and the collaborators. And actually, using the charge neutral topological insulator, the combination of the bismuth antimony telluride in thin films, we have recently produced a normal quantum Hall effect. And it's near the 10 Tesla, it's quantized, and also the conductance is so very close to zero. And this two-parameter scaling flow is less than towards this region. And it's an up and down surface of the half quantized state, we believe. But even more exciting news was released from China. The Professor Xue's group, in collaboration with the Suchan Zhang and other collaborators, they observed a zero-field quantized anomalous Hall effect. And it's a chromium-doped one. Chromium doping undergoes the materials, maybe 30 Kelvin Tc. And below that point, they observed the quantization of the anomalous Hall effect. And this was also reproduced by other groups, including ourselves. And by gate tuning, this compound also nicely showed this kind of the renormalization flow. Okay, this is my conclusion. And I just showed many interacting electrons can feel the emergent electromagnetic field. And from now, in the field of the magnetism, important topics is, I believe, that it's how to create, amplify, and also utilize this emergent electric and magnetic field in the future. Thank you for your attention.